Scanning probe microscopy refers to a group of imaging techniques that collect images of a sample surface by moving a probe over that surface in a raster pattern. As the sample moves, the probe records the height of the surface. Scanning tunneling microscopy was the first scanning probe technique developed by Binning and Royer in 1982. Atomic force microscopy is the most commonly used scanning probe technique. Tapping mode microscopy, magnetic force microscopy, electric force microscopy, frictional force microscopy, and near-field optical microscopy are a few examples of the long list of scanning probe techniques in use today. All scanning probe techniques have a small probe, a feedback method, and fine control of the distance between the tip and the sample surface. Various methods are used to send a signal to the feedback. The feedback control assesses the distance between the tip and the sample. If the distance is too small, the feedback loop signals a piezo crystal mounted at the base of the sample to contract, lowering the sample. If the distance is too large, the feedback loop signals the piezo crystal to expand, raising the sample. An image of the sample is created by plotting its horizontal and vertical movements as the tip scans across its surface. An image of the feedback signal is also produced. This indicates how well the feedback loop is controlling the tip-sample interaction. A scanning tunneling microscope consists of a conductive metal tip positioned approximately 10 angstroms from a conductive surface. An electrical potential of 10 to 40 millivolts is placed between the tip and the sample. This creates a conductor, insulator, conductor structure with an insulator thickness of 10 angstroms. Quantum mechanics predicts that a small number of electrons will tunnel through a short barrier. The number of electrons, or the tunneling current, is related to the barrier thickness. When the barrier thickness is less than 10 angstroms, the number of tunneling electrons increases, strengthening the tunneling current. When the barrier thickness is greater than 10 angstroms, the number of tunneling electrons decreases, weakening the tunneling current. A constant current STM image is created by scanning the STM tip over the surface, while keeping the tunneling current, and therefore the tip sample distance, constant. The tunneling current is monitored by a feedback loop. The feedback keeps the tunneling current constant by raising and lowering the sample stage, which in turn keeps the distance between the tip and the sample constant at 10 angstroms. The topography image is a plot of the movement of the sample up and down under the tip, while the current image results from plotting the actual tunneling current. Atomic force microscopy uses a silicon nitride tip mounted on the end of a silicon cantilever spring. Feedback is based on a change in force between the tip and the sample, which changes the angle of the cantilever and moves the spring. A laser reflecting off of the back of the tip moves up and down on a detour as the spring moves. The feedback loop reacts to a change in laser position by adjusting the height of the sample in order to keep the force constant. The topography image is created from the path of the sample moving up and down, while the deflection image is based on the deflection of the tip. The AFM operator adjusts the feedback controls to minimize the deflection of the tip, increasing the accuracy of the topographic image. Tapping mode is used to image soft samples that could be damaged by the nanonewtons of force that are present in atomic force microscopy. As the name implies, the tip oscillates as the sample is scanned. The amplitude of the oscillation is used as the feedback signal. Tapping mode is used to image soft samples that could be damaged by the nanonewtons of force that are present in atomic force microscopy. As the name implies, the tip oscillates as the sample is scanned. The amplitude of the oscillation is used as the feedback signal.